Hello, this lecture will be about concepts and generic knowledge. Outline of today's lecture, we will go over concepts, we will then talk about prototypes, followed by exemplars and how both of these are similar but slightly different. We'll then talk about the difficulties with categorizing via resemblance alone. Further, we'll move into concepts as theories, and finally the knowledge network. Starting with concepts. Well, in order to function in life, one needs knowledge, and in order to have knowledge, one must have concepts, because it is ultimately concepts that build knowledge. And while concepts such as shoe or house or food or dog seem simple, a lot of cognition could not proceed without them. And if one really tries to grapple with what those things are, as simple as they seem, it actually turns out to be more elusive than one would think at first glance. So what defines a concept? Well, let's take a dog, for example, much like those two nice dogs up there in that picture, even though maybe they're a little bit small on your screen, but nonetheless, they're two dogs. Dogs typically bark, they have 4 legs, and they wag their tails to show different types of, well, how they're feeling, I suppose. And what if they were missing one of these features? Would they still be a dog? So we have probably all seen, as sad as it is, a 3-legged dog, and we still call them dogs. And when I talk about a 3-legged dog, you have no trouble understanding that it is still a dog. We do also have dogs that don't really have much in the way of tails, either by accident or because humans perceive that as more attractive or functional or however it goes. And there are even some cases where dogs don't bark. In fact, the pictures up there are called Basenjis, and they are barkless dogs. Crazy. Anyhow, oftentimes terms denoting concepts can be used easily and often, so like how I've been talking about dog a whole bunch in this slide, but they resist being defined easily because, well, what is dog nest, so to speak, or house, so on and so forth. And in a lot of cases, one can come up with a lot of plausible definitions. These dogs are sort of animals that bark and have 4 legs and wag their tails. But it is oftentimes easy to find exceptions to those, as we just did for barking, having 4 legs, and wagging its tail. And you could come up with even more sort of nuances about what defines a dog, and oftentimes one can come up with these types of exceptions. And one that pops into mind that seems without exception would be dogs are mammals. And, well, that is true, and I don't think there exist any dogs that are not mammals, but mammals by themselves don't adequately describe what dogs are, because manatees are also mammals, I think, and so are elephants, and so are the big cats, and so on and so forth, and those are distinct from dogs. So it works by either showing that certain concepts can exist without a specific feature that we use to define them, and sometimes features we use to define them are not specific enough for that particular concept. So it makes more sense to think about this in terms of probabilistic similarity. And what we mean by this is just it is sort of close, or it matches closely enough, or something to that effect. Or this more eloquent sentence that states, dogs usually are creatures that have fur, 4 legs, and bark, and creatures without these features are unlikely to be dogs. So notice in this way we're hedging our bets. We're saying that most of the time dogs in fact have these characteristics or features, and if they don't have those particular sets of characteristics or features, then they're unlikely to be dogs. But they could be a dog. They're hairless dogs, which is funny that we call them hairless dogs even though it's fur. So wouldn't it be better to call them furless dogs? Well, anyway, the important part here is the usually and unlikely. This idea of probabilistic sense of it is probably a dog if it matches enough of the features I perceive a dog having. So another way to think about this is actually family resemblance. And so while it's often fairly easy to determine if a set of people are related, i.e. they're family members, they rarely share the same set of features across all individual members of the family. And by that I mean all members having the same type of nose, the same type of eyes, the same type of hair, so on and so forth. They are, however, common features that are across multiple subgroups of a family unit, for example, and we could think of those subgroups as sort of the mother, brother, and sister in one case, or the father, sister, and grandmother in another case, or so on and so forth. It can be compartmentalized however you would like. And here what we're interested in looking at is, do these small subsets share certain types of features? So in this case, for example, the mother, brother, and sister could all share the same shaped eyes, while the father, sister, and grandmother could all have the same hair. And now note that the sister is in both of these groups, but that is ultimately one of the ways in which the entire collective is described as resembling each other, because they share sets of features across their various subgroups in this sort of larger domain. And as I've mentioned already, right, there might be no features shared by all individuals, but one can identify specific common features for each subcategory of this group. And the more of such features an object or individual has, the more likely one is to believe it belongs to a specific category. So going back to this family analogy, it is probably not the case that one group has hair in common and one group has ears in common and they have nothing else whatsoever in common. Chances are each family subgroup has a few different features in common, and this is sort of mixed up across the different subgroups. And while we have things in common even with complete strangers, we tend to have much less in common with them on average than we do with our close relatives. So an example here is in this illustration, and here you can see a group of people, and they are, well, all family related, I guess. And here you can see, though, that they don't all look the same. They all do have beards in this case, but their beards are different colors. All of them have noses, though their noses aren't all the same, even though there are a few different types of noses, and some wear glasses and some don't. But you can also see that there is an overlap across these features. So I'll just turn this on for a second. And so see, you can see light-haired glasses and matching light hair but no glasses. So this person can easily be said, okay, these two match. These two have the same eyes and the same type of nose but different types of hair color. Whereas, for example, now this person has the same hair color as this one and the same nose, but this one now wears glasses, which matches with our original person who is also wearing glasses, has the same nose, but has different hair color. And so in this way, we see that there is an overlapping set of features, and the greater the degree of this overlap, the more likely we are to think that that group of individuals all belong to the same category. Okay, moving on to prototypes. So some terms to get into before we go through this section. A prototype is an idealized form of a concept. It can be conceptualized as the average of all various category members that have been encountered by an individual. What this means is all the occurrences in which you have been exposed to a particular type of stimulus in your life, all the iterations of that, if you were to imagine somehow being able to take an average of such a thing, that average is what your prototype truly is. You have seen most likely many apples in your life, sweet ones, sour ones, big ones, small ones, mushy ones, crisp ones, so on and so forth. And when you think about apple, though, chances are you are not necessarily thinking about all of these specific types of apples, but rather you have a generic concept of apple that is kind of similar to all the different ones you've come across, and that sort of average of all apples is what we would call a prototype. Now, it is important to note that these can be different based on the individual who holds the prototype, which should make sense if this is determined by all of our life's experiences and it is an aggregate of all of our life experiences. Each of us has had different life experiences, and so those aggregates are likely to be different for different people. That is not to say they cannot be very, very similar. Many of us probably have a very similar prototype for apple, and in most cases that apple is going to look a whole lot like apples we see in cartoons. Moving on to prototype theory, this is the idea that the best way to identify a category is to specify its center rather than trying to define its boundaries. So if you think back to when we were talking about what a concept was, we were looking at the various features that define the boundary lines of a certain type of concept. Like for dog, it barked and had 4 legs, so on and so forth. Prototype theory advocates the idea of using sort of the central prototype of dog and then looking at how far different pieces or items match that prototype and using that distance to define whether it is of a certain category or not. This leads us to this idea of graded membership. Graded membership is the idea that the distance or difference in resemblance an item has to the prototype will determine its membership, and that membership is ultimately a matter of degree. And what this is saying, and I'll show you an example about this in a minute, of different types of individuals that fit into a category are better examples or worse examples of that category. And so let's just jump into that. So here is a picture of a set of dogs. They are all, in fact, dogs. This is not a trick in any way. And just think about it for yourself for a second here, but out of these 6 dogs, which one is the most dog-like? Also, please take a moment now to just marvel at the fact that even though they're all dogs, and I asked which is the most like a dog, chances are you have no trouble coming up with an answer to that question. Which, if you really think about it, is a little bit strange because they are all dogs. They fit into one category, yet we're saying some are better representatives of that category than others. That idea is what graded membership is. So just moving on that, you could also pick out which one is the least dog-like, and you could actually order these set of 6 dogs on a scale from least dog-like to most dog-like, and chances are you would have no trouble doing this. Okay, moving on to some support for prototype theory. So first of all, they use something called the sentence verification task. And in this task, participants are basically asked to determine if sentences are true or not. And they're given sentences such as a penguin is a bird or a robin is a dog. Obviously, a penguin is a bird is true, and a robin is a dog is false. And so you could just imagine yourself in this place. You would sit there with either 2 buttons or on a keyboard, also using 2 of the buttons of the keyboard, pressing one to indicate truth and one to indicate false, and then the experimenters would measure your reaction time to these responses. Now, the interesting part comes in that participants are faster to respond in some cases than others. So for example, participants are faster at responding to a robin is a bird than they are to responding to a penguin is a bird. Now in both cases these are true, and in both cases ostensibly their finger is resting on the key, and these sentences are pretty simple, and so they should be pretty even, but they're not. They are consistently faster at responding to a robin is a bird as opposed to a penguin is a bird. You see the same pattern for sentences like a German shepherd is a dog versus an Afghan hound is a dog. And ultimately, the closer the sort of object of the sentence is to a prototype, the faster they're able to respond to those sentences. And the further those sort of targets of the sentence are from those prototypes, the longer it takes them to respond. Another form that gets used is this idea of the production task. And in this task, it asks participants, well, it doesn't, the experimenter does, but participants are asked to name as many items from a specific category as they can. So this would be as if I said furniture to you and you tried to list down all the various items that fit with furniture. And chances are right now you couldn't help but think either table or chair. Anyhow, the idea here is that participants will first locate the correct prototype in memory, and then they will consider what resembles it. So just like I said, furniture, you will locate this sort of furniture prototype, and then you will look at what pieces fit close to this prototype of furniture. So in this case, the idea here is that members, so these are the actual pieces that resemble this prototype, that are close to the prototype itself should be named before members that are farther away from that prototype, on average, of course. And this is largely what empirical data shows. So how to make sense of this table, I will just turn this back on. So these are 2 separate ones. This set here is for fruit, so the prototype in this case is fruit, and for this the prototype is bird. And here you can see that most people were able to name apple first, and then they sort of named them in this listing, followed by same thing for birds. The ratings on this side, they refer to how closely these items resemble their various prototypes. So in this case, the average rating given to apples is 6.25 out of 7, indicating that this very closely resembles the prototype, whereas let's say a pumpkin only received a 2.3 out of 7, meaning it is very far from this concept of prototype, and you can see that it was not named near the top very often. You find this same pattern for birds, where a robin and a bluebird are very high, whereas an albatross and a penguin are quite low, and I don't actually believe that a bat is a bird. Anyhow, finally, rating tasks. This refers to those ratings in a way that we were just giving, and it also fits with the idea of graded membership. So ultimately, what I asked you to do in that final question of the graded membership example of putting a sequence of those dogs from least dog-like to most dog-like or vice versa is ultimately what these types of tasks are all about. And participants are able to make such judgments quite easily and are fairly consistent in their ratings. So what we mean by that is if you were actually asked to sort those dogs out into most dog-like to least dog-like, you would be able to do so fairly easily. And if I was to ask you to do it again in a month and then in a year later, chances are your ratings would be very similar over time. Further, these ratings ultimately support this idea of prototype theory, where again members closer to the prototype receive higher ratings than members further away from the prototype. And ultimately the previous 3 slides are giving support for this idea. Now, one topic to talk about before we move into exemplars is this idea of basic level categories. And so not only are certain members of a category privileged, such that they're closer or further away from this prototype and are named more readily when they're close to the prototype, or one can respond more quickly when they're close to the prototype, but some prototypes are actually privileged over others. So entire sort of main concepts in how we order and understand the world. Sort of a meta prototype, or prototypes of prototypes, kind of. Now, basic level categorization is a level of categorization hypothesized as the quote-unquote natural and most informative level, neither too specific nor too general. You could think about Goldilocks here. So a way to demonstrate this is, what would you call what is in this picture? I'm going to bet most everyone who actually responded, which maybe you did in your head because responding to a computer screen is kind of weird, but many probably said chair. Now, why not an upholstered armchair or just furniture? Both of those are ultimately concepts as well, but we would consider those concepts that are not at this basic level of categorization. So in this example, chairs or chair would be that basic level category. And you can see how this fits with this definition we've given of basic level categories and what they're hypothesized to do. To say chair, it's pretty easy for other people to understand what you mean, and it can either be filled on or left as is based on the conversation itself. But to say upholstered armchair could add miscellaneous information that is not necessarily relevant to the conversation or knowledge piece at hand, and using something as generic as furniture doesn't really give that much information if you wanted to talk about the particulars of a chair. So in this case, chair is that happy middle ground or Goldilocks description of category. Okay, moving on to exemplars. So some terms for this section. Exemplars are a specific remembered instance. So this is perhaps the biggest difference between an exemplar and a prototype. So it is possible for the prototype, that aggregate, to coincide with a remembered instance. For exemplars, however, the exemplar must be a remembered instance. There is no averaging, there is no sort of happy middle ground of non-existence, so to speak. Exemplars are examples. They are things we have seen before and we remember. So For exemplar theory, the standard is provided by whatever example comes to mind in the context in which it is required, thus context specific, meaning even you yourself will have different exemplars for the same concept depending on where you happen to be. Next, we have exemplar-based reasoning. This is reasoning that draws on knowledge about specific category members rather than drawing on more general information about the overall category. So what this means is when we're thinking about dogs and we were using exemplar-based reasoning, we would be thinking about particular dogs, not just dogness or the dog concept, which would be this more general overall category. So, typicality data, this is going to talk about how closely matched various items are. So in this task, participants were asked to determine if each of a series of photos is a fruit or not, and then their response times were measured. So this is very similar to the sentence verification task where people read sentences and they were asked to report on the truth or falsity of those sentences. In this case, very similar, yes or no responses, 2 pictures shown on a screen, deciding whether they are fruit or not. Now imagine you are a participant and you are shown an apple or a persimmon. And well, we'll just imagine you're shown both in this case, one after the other. So apples are a common experience for most. We mean this by saying that almost everybody has come across apples many times in their lives. And thus searching your memory for apples to compare to this image you're shown on the screen will be very quick and easy, and your response times will tend to be fast. Persimmons, on the other hand, are much less common. Most people don't interact with them regularly, many people don't see them often, a lot of people don't even know what persimmons are. And thus, memory searches will tend to be difficult and effortful, and response times will tend to be slower. Now, of course, you could put forth similar explanations based on prototype theory, that an apple more closely resembles a prototype of fruit than a persimmon, and thus we were able to respond more quickly to apples than persimmons. And that is ultimately true, and none of the evidence supporting either exemplar theory or prototype theory so far can actually support one over the other. Many or much of this data is ultimately agnostic to which type of theory one is after. And as one sees oftentimes in science, the truth is a little bit closer to both. So when it comes to exemplars and prototypes, prototypes provide an economical representation of what is typical for a category. Remember, they're giving us sort of an average of all of our experiences. So it makes it very easy to understand sort of a huge history of exposure to a certain type of thing very, very quickly, because it is ultimately just this average of all of the items we have come across in our lives. And this is very useful in circumstances that require very quick summaries. By this, I just mean we have to act or behave in a certain way, and time is limited, and so having a general conception of what we're supposed to do will oftentimes help us. Just think about when you walk into a restaurant, you don't need to know the particulars of how to behave in every single restaurant individually. Rather, you have some basic ideas of how to behave in a restaurant, and for the most part, that will get you through what you need to do. Exemplars, however, provide information that is lost from the prototype, and this includes information about the variability within a category. Now, with the prototype, there's an average. We've gotten rid of the individual information to give us sort of the core piece of whatever this concept is, while the examples or exemplars ultimately allow us to have a more nuanced view, but we will lose sight somewhat of the whole when we are paying attention to exemplars. Now, conceptual knowledge includes both prototypes and exemplars. So an example here would be a person may have very extensive knowledge of a certain field, in this case, let's say horses, that's the example in your textbook, and thus they might have many exemplars for horses, right? If you have very extensive knowledge of horses, you have seen many horses, you've read about horses, you might have trained horses, so on and so forth, and there are many, many particular examples you could draw from. On the other hand, the same person might have very little knowledge about a snowmobile, or any other field really, and thus only have very general information about it. That general information is ultimately represented as a prototype, There are not very many specific examples available, there's not very much knowledge about them, and chances are we only have a limited understanding and set of items to work from that were not very highly remembered in the first place, and what we're left with is sort of a general understanding of what snowmobiles are. That general understanding is a prototype. Note, going back to the earlier explanations of both of them, prototypes are great for if we wanted to know what a snowmobile was. It's a vehicle to get us over the snow. Great. But it does not allow us to know about the particulars of snowmobiles. What's the difference between, say, snowmobiles that have one tread and two? What type of snow is it okay to be on with certain types of snowmobiles, and so on and so forth. That is not information you could get from a prototype, yet someone with detailed knowledge, with many exemplars, would be able to call forth that type of information. Basically, for all people, the pattern of knowledge ultimately might depend on the size of a category and how confusable the category memories are with one another. So if they are very confusable with each other, chances are one will not have lots of examples or exemplars to work with, and instead one will have a prototype, because if they're all confused and mashed together, that is ultimately what the prototype is. Further, the size of a category will also impact this as well. If there are only two instances that make up a category, easy to remember examples of both. If there are a little over 2 million different types in a particular category, chances are it is next to impossible to remember all the individual characteristics of these different subsets, and therefore one is more likely to rely on prototypes. Now let's talk a little bit about the difficulties of categorizing via resemblance alone. So, some terms for this section. Typicality, this just refers to the degree to which a particular case is typical for its kind, or how closely it resembles the average of its kind. Resemblance is a way in which two or more things are alike. Categorization is the action or process of placing into classes or groups. And finally, anomia is the inability to name common objects. It is oftentimes associated with certain types of brain lesions. We'll talk about that at the end of this section. Okay, differences between typicality and categorization. So typicality and category membership do not always go together. So we have been talking about prototypes and exemplars and how the closeness to those prototypes ultimately determine how easily we can process information about those categories and concepts. Even though they might go together in many cases, they are not the same thing, and there are situations in which they do not work together at all. In fact, we would say that they're completely independent of one another. So in a task, participants were given a list of numbers and asked to rate how even each number was. Another set were given other numbers and told to rate how odd those numbers were. And not odd as in strange, but odd as in they were an odd number, the opposite of an even number. And interestingly, participants were very consistent in these ratings, and they were about as consistent in these ratings as they are for rating things like how bird-like are birds or how fruit-like are fruits, or very similar to how we rated the dogs in the early part of this lecture on how dog-like they were. Now, ratings of typicality were ultimately independent of categorization. So when it came to categorization, all participants could ultimately categorize the sets of numbers they were given as being either even or odd, which is fairly easy for most of us to do, and accuracy ratings were very high. But ratings of evenness or oddness did not quite work so cleanly. So here you can see the set here is for even numbers, set here for odd numbers, and ultimately they parallel each other. So I'll just talk about the even numbers. So here you can see that, again, I believe this is rating from 1 to 7, with 7 being the most typical it can be and 1 being not typical at all. And here you can see a 4 has a typicality rating of 5.9, meaning it is very typical of an even number. But as you move away from those lower numbers, ostensibly 2 being the most typical of an even number, you can see that 8 is less typical or less even than 4, and 10 less even than 8, and 34 even less than that, and 106 being the least quote-unquote evenness of all the even numbers given. And weirdly enough, that probably kind of makes sense, which is kind of crazy to think about. But it also shows that ultimately the process of categorizing is not as simple as just it is close to what the average of that group is and therefore it belongs to this group. Because from this data you can see that there are things that are almost not at all typical for their group, but we have no problem categorizing them into the correct group. What about when it comes to changing categories by making them more or less typical to the group that we're comparing them to? So here's an example to illustrate this. Consider a lemon, for example. So a nice yellow, fresh lemon. Now, imagine painting this lemon white and adding some red stripes to it. So it just kind of looks like a circus lemon now. Now you take a syringe full of sugar water, or simple syrup, and you inject this lemon with that sugar solution. Now you go outside, you put this lemon on the road, and you get into a truck and you run it over a couple times so it's as flat as a pancake. Now, is this striped, artificially sweetened, flattened lemon still a lemon? Or is it now something else, a non-lemon of some kind? And I would put down a penny right now betting that most of you will say that it is still a lemon. Despite the fact that it's striped and sweetened and flattened, it's still a lemon. It didn't lose its lemonness by all these various things we did to it. Another example now, to go in the other direction, let's consider some counterfeit money. Now, a bill is given to you and it is very skillfully produced and bears a nearly perfect resemblance to your prototype for legitimate money. For all practical purposes, you cannot tell the difference, other than I have said this is a counterfeit bill. Is it actually real money, or is it just paper printed to look like money? I mean, yes, it's probably like cotton or some fabric or whatever the heck money is actually made out of and not paper, but the question remains. Even if it matches your prototype of money perfectly, does that make it into money, or does it remain some counterfeit thing? And ultimately, this shows us that categorization must depend on something more than just typicality, because that counterfeit bill is about as typical of a counterfeit or any kind of monetary bill as you could get. It looks pretty much perfectly the same, and that lemon is about as atypical for lemons as you could get. It's the wrong shape, the wrong color, the wrong sweetness. I mean, it just doesn't really match the lemons at all, yet we still call it a lemon without any trouble whatsoever. So, what's going on? That takes us into our next section, concepts as theories. So, the complexity of similarity. When thinking about categories, when one is not guided by typicality, we tend to focus on attributes that are believed to be essential for each category. And we'll talk about what counts as an essential category in a minute. And judgments about those essential categories ultimately depend on one's beliefs about those categories. So here is an example of plums and lawnmowers. So in this case, are plums and lawnmowers similar to each other? And most of you would say they are not. But if I was to sit down and have you count the similarities that exist between plums and lawnmowers, we could come up with many of them. For example, both of these things are probably less than $1,000. Both of them exist on Earth. You can buy both of them at a store, maybe not the same store, but nonetheless at a store. Both of these things can oftentimes be found on farms, and you can keep going. Both weigh less than a ton, and then I could just be silly like that and iterative and say they're less than 2 tons and less than 3 tons and 4 and 5 and so on and so forth. And we could come up with huge lists of why plums and lawnmowers are the same color. I mean, not the same color. I was thinking of a plum-colored lawnmower there. Anyhow, the similarities between plums and lawnmowers could be so many. But chances are you're not going to believe me when I say that plums and lawnmowers are similar because both of them weigh less than a couple of tons. Because that feature is not really essential to being a plum or a lawnmower. When we think about plums, we think about sort of their fruitiness, whether they'll be good for baking, whether they're ripe enough to bite into. Lawnmowers, on the other hand, are about how well they chop grass, and we couldn't care less about whether they're tasty or not. And neither of those situations really call to mind that they weigh less than a ton. Who cares that they weigh less than a ton, right? Ultimately, what we're talking about here are essential categories. Now, resemblance depends on whether objects share important and essential properties, not irrelevant ones. All those ones I gave somewhat jokingly of less than $1,000 and less than a ton and found on Earth and so on and so forth are irrelevant properties. Plums and lawnmowers don't share a lot of essential properties. Now, decisions about these ultimately depend on our beliefs about whatever concept is in question. What do we believe about lawnmowers and plums? And this will dictate how we define our important or essential properties. And ultimately, the use of prototypes depends on our ability to make judgments about resemblance. And so where this is going ultimately is that the use of prototypes and what prototypes we have and how we define and build these prototypes is a largely interactive process with our own beliefs of how the world is supposed to be. So, expanding on this, we'll start talking about explanatory theories or concepts as explanatory theories, and many people in this field consider that each of us ultimately has our own theories about all the concepts and categories we have. All of us have specific notions about how those categories work and what makes them and what they're allowed to do and not allowed to do and so on and so forth. And so specifically these categories are, like I mentioned, they're theories about what these categories are and how they act and why they are as they are. And these implicit theories ultimately influence how we categorize things, right? Remember the lemon and the fake money. So for the lemon, all of the features we changed didn't change its lemonness. Whereas if I was to say that I have a lemon that looks exactly like a lemon and tastes exactly like a lemon, but I have modified its genome, so its genome is entirely different than an original lemon. Chances are now it would be easier to say it is no longer a lemon. Most of this is around our theories of how lemons work. We believe that lemons are built from the various genetic information that is presented in them. That is how they came to be. By making a synthetic one is not necessarily a lemon, especially if it has different genetic coding, because we tend to believe that genetic information is highly relevant to what defines a biological category. This ultimately also is very important when we're talking about the new possibilities for a category. So I'm going to give an example about airplanes in a minute, and that hopefully will make this more clear. Finally, our theories also impact how quickly we can learn about new concepts. So our theories ultimately allow us to tie many concepts together and form integrated units. And if you will remember to when we were talking about learning, it is much easier and more effective to learn when you have lots of other information in which to embed it. By having theories, we are able to organize vast amounts of disparate concepts we have into sort of unified narratives. Those unified narratives are much more easy to understand and learn because they make more sense to us. Sort of now going back a step, so this idea of using our theories to think about possibilities for a category. Take, for example, an airplane made out of wood. Could it fly? Maybe if it wasn't as big as the 747, but chances are you can imagine a wooden airplane that can fly. Probably because there are some wooden airplanes that can fly. But what if it was made out of ceramic? Well, probably not, because ceramic is hard and heavy and not quite what planes are made out of, but it is hard and metal is hard too, so maybe it could fly. But whipped cream? Probably none of you are having trouble saying that a whipped cream airplane could not fly. Maybe, but probably not. Further, would a plane still be a plane if it was made out of whipped cream? Well, probably not. Chances are now what it is a sculpture or a birthday decoration or some crazy blob of whipped cream that happens to look like a plane. In all of these cases, chances are you would not call them or it an airplane. And how is this working? An airplane, or our theory of airplanes, is they must fly, they must be able to conquer gravity, and they're made out of specific materials. Wood fits closely with those ideas of materials, ceramics loosely, but is not too alien. Whipped cream does not fit with that whatsoever. Further, on the other side of this coin, a simile of a plane made out of whipped cream, while it may look like an airplane, probably will never be called an airplane because of our theories of what whipped cream is used for and how it behaves. Ultimately, our theories of how these concepts work largely define how we will understand our concepts and prototypes, and it will further dictate how we will use those concepts and prototypes in future occurrences in novel situations. When it comes to making inferences based on theories, this also now has a big impact on how we will incorporate new pieces of information. So, categorization ultimately enables one to apply our general knowledge to new cases that we may encounter. So, if you were to all of a sudden see a light that was flashing red and then turned green for a little while and then started flashing red and then started going green, you would probably not have much trouble understanding that the system is either having trouble when it's red and working when it's green, or asking you to stop when it's red or go when it's green. And even if you have no idea what that machine is, even if that machine was just a little box with two lights in it set to blink randomly, in those cases, you will infer what the function or meaning of those lights are based on your previous information. Further, categorization ultimately allows us to draw very broad conclusions from our experience. Now, if you read the first prologue of this chapter, they will talk about people with perfect memories, people who remember every single instance of their lives from some point onwards. And before you think about how cool that is, it ultimately is not something that most people who have it seem to enjoy very much, because one, they're constantly stuck in the minutia of all of their memories, but what's worse is they are actually unable to form these broad conclusions, because whenever they're thinking about a dog, they can't actually think about just the generic dog. They think about every instance of dogs that they have seen. And not only that, but for an individual dog, they think about all the different aspects and places and directions from which they have seen that dog. And it becomes very difficult for them to actually understand the general idea of a dog. And if you take a couple minutes here to just stop and think about how useful that general conception is, well, that could be severely detrimental to life if that was taken away from us. We'll talk a little bit now an example about how these sort of inferences ultimately can be biased. So here, when participants are told that a gazelle has a certain enzyme in its blood, people are fairly likely to say that lions will have this enzyme in their blood as well. Conversely, if you're told that lions have some enzyme in their blood and then asked to say whether or not, or how likely it is, let's say, that gazelles have this enzyme as well, people are less likely to say that gazelles have it when it was presented as after the lions having it first. Whereas vice versa, when gazelles had it, then it made a lot of sense to people that lions will have it too. Then why is this the case? Well, it's related again to our theories about these concepts, and those theories on those concepts define how we make inferences, right? Just think about who eats whom. It is lions that eat gazelles, and we believe that eating something incorporates it into ourselves, so it's easy for us to understand how the enzyme could get into the lion, but gazelles don't eat lions, so there is no way that we think that it could be in the gazelle if we're told it's in the lion. And notice how we're thinking about this in terms of this predator-prey relationship. This is how we conceive of these concepts. We're not necessarily thinking, when we're thinking about gazelles and lions, in terms of just the higher order mammals, and that maybe this is an enzyme present in all mammals. Interestingly enough, the same goes for cows and grass. If told there's an enzyme in grass, people will readily say that it is in cows as well, but if told there's an enzyme in cows, they will be resistant to say that it is in grass as well. They are also different profiles for different concepts. And so we do tend to, at a very basic level, think differently about naturally occurring items versus human-made objects. This is oftentimes, or human-made objects are oftentimes called artifacts. This is due to having, again, different beliefs about why categories of either sort are the way they are. We believe that naturally occurring things are the way they are for different reasons than we think human-made things are the way that they are. And further, in general, we tend to assume that there is a higher degree of stability and greater homogeneity when thinking about natural things than when reasoning about human-made things. Another way of thinking about this is we think natural things tend to be more similar in nature than human-made things, or that human-made things have much higher variability than naturally formed things. These differences can also be seen in how we characterize concepts. So some are characterized in terms of their features. These are the types of concepts we have spent most of this lecture talking about: dogs by barking and birds by flying and so on and so forth. But other concepts involve some type of goal-derived category. So exercise equipment would be a good example of this, and exercise equipment might not have very many features in common, nor really any features in common at all, but all of them serve to allow us to train our own fitness and health, and so it is that goal of getting healthy that defines this set of disparate machines as belonging to a single category. Further, some concepts apply to relational categories. For example, hunting. In this case, when we're thinking about the concept of hunting, there's often some type of predator and some type of prey. Something is hunting and something is the hunted. Whenever we think about this concept of hunting, we're ultimately thinking of some type of relationship. Finally, some concepts apply to event-based categories. So these are things like shopping trips. There can be many different kinds of shopping trips. People could walk down to the corner market, people could drive to the store, people could go to outlet malls next to Las Vegas if they felt like it, and all of those things are very different, but they're ultimately all shopping trips, or easy to define in that form. And so these are concepts that just apply to some type of event. And this yet again shows that there are many different forms of concepts, and we tend to think about them all in slightly different ways. A little bit about brain regions relating to these different profiles. So it has been found that there are different brain sites activated when we are thinking about living versus non-living things. Interestingly enough, this is also one of the earliest distinctions that young children learn to make when they're observing their worlds. Further, we also see differentiation in brain regions when people are asked to think about or observe tools versus natural objects. So items like a hammer versus a rock. Now, the loss of naming in anomia is often specific to certain categories. And what I mean by this is that sometimes people will no longer be able to name objects that are living, but will have no trouble naming objects that are non-living. And sometimes this pattern is reversed. And sometimes it will be even freakier than that, where some individuals will lose the ability to name fruits and vegetables, but still be able to name other living things and non-living things as well, which is pretty crazy at the end of the day. Here is just a nice little image to demonstrate this. So let me turn on my pointer again. Okay, so these three here, these modeled brains, are ultimately showing three different types of lesion data. So the red marks are showing highly overlapping sets of lesions, and as you're moving away from red, less overlap. So for people here who had trouble naming persons, they had a tremendous amount of damage right over here. Whereas people who had difficulty now saying or naming animals, you can find that the most concentrated was right there, and for tools it was even further back. Now, reading this here, this is just superimposing the categories of where we had damage. This just corresponds to these three, the blue being this one, the red being this one, and the green being that one. Sorry if you're colorblind, this color in the middle is red and this one is green. So when lesions are here in this portion of the brain, you can see that accuracy rates for being able to describe people when shown is quite low. So 60 out of, let's say, 100 here. They can easily describe animals and tools, or not describe per se, but name them. For those with damage here, they had trouble now naming animals, but you can see that they also had trouble naming persons. Chances are this is largely related to there being overlapping sections of damage, nor are there hard lines in the brain. Finally, here you can see that they were able to, at a high degree of accuracy, recognize people and animals, but they suffered when it came to recognizing or naming tools. And this just shows that different parts of the brain seem to be involved in the understanding and management of different types of concepts. Now, it is important to note here that this does not necessarily mean that different concepts are stored in different parts of the brain, nor that these parts that we're talking about, as in these right here, are somehow the containers for these items. First of all, if that was the case, you would not see relatively high accuracy rates, right? This is 60%, which is still pretty good versus 0, right? So these are just showing that there is damage. This damage is causing interruptions to specific brain networks, and that damage is ultimately resulting in this impairment. But we don't always know what those networks are and if those networks are actually fundamental, or if just damage all around is slowing down the system, which is causing this damage to happen. That being said, it is pretty cool evidence to see that different types of lesions cause different types of impairments, leading at least somewhat support to the idea that different parts of the brain are responsive to operating on different types of concepts. Finally, we get into the knowledge network. Some terms, this is a little bit more term heavy than the last few sections. So local representations, we're talking about how information is stored in the brain or an artificial network in this case. So a local representation would just be a representation in which the information about some item or stimulus or concept is encoded in a small number of identifiable nodes. This is kind of the idea of the grandmother cell, that there is a cell that encodes for your grandmother. I don't think there is actually such a cell, but that would be a local representation. So these are often spoken in terms of this idea of one idea per node or one concept per location. So much like a file drawer or a little jewelry box in which each different type of jewelry has its own little box or container. This is often contrasted with distributed representations. So this is when representations of ideas or concepts don't have one particular place in which they're stored, but rather they are represented in a mixture of activation across many different units. And it is that pattern of activation or activity across these units that is ultimately what the representation is. Now, the same nodes also may participate in many other patterns, so no one node is truly part of any one representation. It is how all of the nodes are either active or silent and how that is mixed together that ultimately defines a representation. This is called distributed representations, and much of the brain seems to work on this format. We also have this idea of connectionism, and this is the approach to theorizing about the mind that relies on parallel distributed processing among elements that provide distributed representation of the information being considered. Okay, a couple of things here. So connectionism, there are a lot of people who fall under this camp. It became popular in the last 40 years. Parallel distributed processing just means that you are processing multiple different types of information and steps of processing information all simultaneously across many, many different units, all in synchrony or all in parallel. And these provide distributed representations because you're doing processing across an entire network as opposed to having singular places of storage upon which things are then operating and then being stored in another particular place. In these cases, the entire system together is both storing and operating on this information. Parallel distributed processing, as I mentioned quickly before, is a system of handling information in which many steps happen at once and which various aspects of the problem or task are represented only in a distributed fashion. So just remember, no one place in which any of this information is stored, and all processing takes place simultaneously. Well, not all processing takes place simultaneously, but in order to process any given unit, all of the parts and pieces required to understand or operate on that conceptual piece of knowledge are all engaged at the same time. Finally, we have propositions, and these in this case are defined as the smallest units of knowledge that can be either true or false. And so this is the idea that guava is a dog, and you could say, no, it is a fruit, so that is false. But if I just said guava, that is not a proposition because that cannot be true or false. Okay, moving through this knowledge network. So this is the same network we were talking about when we were talking about long-term memories. So if knowledge is in fact stored in this memory network, then every time we call on our knowledge, we retrieve information from this network. And this must occur through the spread of activation, as we've been talking about through in several lectures. And the further this activation must travel, the more time is needed to call upon the required knowledge, right? So the more distant it is in that network, the more nodes in line need to get activated as this activation flows, and the longer it takes my activation to get where it needs to go. And thus, it should take less time to retrieve knowledge involving closely related concepts, stuff like a robin is a bird, than for more distantly related concepts, like a penguin being a bird, for example. But we'll talk about even more nuance in just a second. So, evidence for this knowledge network. So here we can see that, or not yet, I suppose. Anyway, participants were shown a series of sentences much like they were in the sentence verification task. Sentences such as a robin is a bird or cats have claws. And then they were asked to indicate if the sentences were true or false, and their response times were recorded. Further, the travel distance between nodes, the longer the expected RTs were. RTs in this case are just reaction times. Now, here let's look at this network, or this simulated network, to kind of get an understanding. Sorry that this is so small here, but in this case we have birds and cats and dogs, and all three of them are animals. And animals have hearts and eat food and breathe and have skin, so we know that cats also have hearts and eat food and breathe skin because cats are animals and animals have these things. Why is it stored like this? Well, because the brain does not necessarily need to store individual instances of every different feature that every different concept has. That's just not quite how the system seems to work. Okay, moving down further, we have robins and canaries are both types of birds, and Cheshires and alley cats are both cats, and collies and terriers are both dogs. And a canary can sing and is yellow. And so if I wanted to know if a canary had a heart, wouldn't have trouble, would just canary activation would flow to a bird, bird's activation would flow through to animals, and that would flow to have hearts. And so I could query this system and pull back the information that yes, indeed, canaries do have hearts. And I should take longer, though, to respond to canaries have hearts than to canaries can fly. Because to understand canaries can fly, I only need to have my activation spread to birds, followed by birds can fly. And here I only have these two steps, whereas to canaries have hearts, I have to go 1, 2, 3. Okay, is this what we see in the data? In fact, it is. Here, or being able to dismantle this graph, here we have the average response times in milliseconds and the number of sort of levels to get traversed. And so you can see that responding to a canary is very, very fast. Don't have to go anywhere. It takes longer, however, to respond to a canary as a bird, which makes sense because canary is a canary, don't move anywhere, versus canary is a bird, have to go there. And canary is an animal, takes even longer, have to move further. When it comes to properties about these, we find the same type of thing. It does take a little bit longer to define whether they are properties associated with a specific concept, like canary in this case, but canaries can sing, very easy. They're associated with singing. Canaries can fly, however. Flying is not unique to canaries, nor I suppose is singing, but both robins and canaries are birds and they can fly, and that takes a little bit longer because I have to move further away from my concept of canary. And finally, canaries having skin takes even longer to respond to because I have to travel further through this network. Note that the difference here is only about 150 milliseconds, but nonetheless, it is a recordable and observable difference. Okay, moving back over here. This does not explain how the sentence verification tasks we talked about earlier also have different prototypes. Penguins and robins, for example, should both be connected to birds. And if I'm talking about both of them being birds, well, I only have to travel the same distance. So why is that the case? Further, there are also anomalies in this data. Sparrows are more prototypical of birds than peacocks are, but we can respond faster to the statement of peacocks have feathers than sparrows have feathers. And this is oftentimes talked about because the association of feathers and peacocks is very high, while the association of feathers and sparrows is not that high. And so one way to begin to understand this is that this network given here is a hierarchical network. There are hierarchies in which these are connected, and you don't see many cross-level connections. The brain, however, is not necessarily organized in this fashion. There is nothing to say that can sing cannot be associated to has claws. You probably wouldn't have that connected, but hypothetically it could be. If you had only ever seen someone sing while they were wearing a glove with claws, maybe you would associate claws with singing. Just like when we talk about peacock feathers, we almost always talk about their feathers, and we talk very little about all of the other things that peacocks have to offer, which is very horrible honking sounds, but they are tasty from what I understand. Additionally, we have propositional networks. So these add additional now information. If I simply had direct connections as I was showing in that previous network, for example, in this case, the very simple network of dog connected to Sam, do I know from just this information whether Sam is a dog or if Sam has a dog or if a dog has Sam? Which I guess technically could also be the case. This diagram or this type of network does not allow us to know the difference between these types of items, and we, however, in general knowledge and discussions, can do this very easily. So there must be now additional information present that allows us to understand this of concepts. So this is where propositional networks come in. Here we're going to understand a little bit about representing knowledge. So all of these sort of ovoid shapes are propositions of some kind. And so here you can see where we'll start with the relationship of a dog and a bone, of how these are connected. So you can just think of dog and bone here as dog and Sam, or the bone is Sam, however you want to think about it. Anyway, the agent is dog. Dog is what does things. Object is bone. The dog does stuff to the bone. Already think of how much more information we have than just here, but we have additionally the relation that defines the agent and the object. So dogs chew bones, dogs being the agent, what they do to the object there is. You can see that this is expanded further, where again we have dog as the agent, which in relation to cats, which is the object, it chases them. Or dogs eat meat, and bones are a part of meat. In this case, it's just bone is the subject, object is meat, and part of is their relationship. In this way, we can have a much more nuanced and rich understanding of how different items are related to one another. Now, we're not saying that the brain has little ovals and arrows, but these are useful conceptualizations in order to begin understanding how these systems might be working. Further, these type of propositional networks can be used to explain episodes or periods that lasted over time. So here you can see that we have sort of this 4-united proposition where Jacob as the agent feeds pigeons, which are the object in this case, and when this happened was last spring, and those pigeons were in Trafalgar Square. Right? So here we can see not only information about pigeons themselves, but how pigeons are related to Jacob and how this proceeded over time. Okay, So now let's talk a little bit about distributed processing. So in networks that use such processing, they must use processes that are similarly distributed so that widespread activation patterns can have broad enough effects to invoke different patterns. What we mean by this is there must be lots of different units working in synchrony in order to have a conceptual understanding of something, and you need that widespread activation because all of it is then required to interact with other units so that a new state of activation can be brought forward, which will ultimately represent some new concept or modification of that understanding. The steps bringing this activation flow about must all occur simultaneously in parallel, because you couldn't have some parts operating and moving forward while others were stuck. Imagine what would happen if your understanding of how peel operated was different than how sweetness operated, and they worked at different times, and how you would try and understand biting into an apple if you processed the skin texture differently than the sweetness of an apple. It would probably be a very weird situation. Finally, if you make such models in a sort of artificial way, those models are often called PDP models or parallelly distributed models. When it comes to PDP models, they have an excellent capacity for being able to detect patterns in the input they receive. So what I mean by this is that you can pump them full of information and they will be able to find patterns. So when you have sort of advanced AI that they talk about that can recognize numbers from handwritten digits, they're ultimately using a form of parallel distributed processing in order to look at the patterns in pixels that allow them to then define what in fact numbers are, even though they don't actually have any understanding of what numbers actually are, just that 8s are 8s and 2s are 2s. They're so good in some cases that they can recognize different sentences having the same structure, meaning that all kinds of sentences formed of all kinds of different words could be defined as run-on sentences or not. They can identify different game positions as having the same next move. So in chess, there can be many different moves or possible moves or game situations that lead to a certain types of crux interaction. Finally, and probably what is most impressive about such networks and why everybody is all kinds of crazy about AI and machine learning these days, because ultimately what they're talking about is variations of these types of models, is their ability to generalize what they have learned to new variations and patterns. After I have trained a model to understand handwritten digits based on the pixels that I have given it that are scanned of these handwritten digits, I can show it digits that it's never seen before, and as long as that input format is correct, meaning I give it, the 16 by 16 pixels or what have you, it will be able to decode and identify those new numbers even though it's never come across them before. This is probably one of the biggest advancements for robotics fields that has happened since we decided to start making robots. Finally, a note about biological plausibility, because one will hear this talked about all the time when it comes to these kinds of neural networks. So people will say that these networks are biologically plausible because the brain is also distributed in how it processes things, but there are a few caveats to this. First of all, many of the computational learning algorithms that get used in these types of networks could not be instantiated as they exist in the brain as we know it. It is simply not connected in the same way, nor does it process memory in the same way as a computer algorithm. Further, when we draw such networks, we tend to use local representations. If you think back to the various networks I showed you, there was robin in one place connected to bird and another connected to animal in another. That is a very localist way of representing it. In truth, that is not how these items are actually represented. They're distributed concepts, but those are very difficult for us to sort of conceptualize. Imagine I gave you 82 random dots on a piece of paper and was like, that's a dog. And then I gave you another 42 random dots on another piece of paper and was like, that is a cat. Chances are you would look at me like I was a crazy person. Finally, a single node in a network rarely, if ever, maps onto a single neuron. When we draw a network of 200 units and it can do all kinds of crazy complex things like recognize digits, that does not mean you could take 200 neurons and make them recognize handwritten digits as well. It does not work in that way. Oftentimes, a single node in a network represents an entire cluster or population of neurons. So while it is true that they are biologically plausible, note that that's something we use to sell them on their sort of capacity nowadays and make them appeal to cognitive scientists. There are some key differences between these artificial neural networks and the brain itself. Lastly, we have a little bit about learning as setting connection weights. So we have talked about this a little bit before, but in network terms, knowing something, having knowledge about something, corresponds to how activation will flow if there is activation on the scene. Meaning, as I'm thinking about some concept I am knowledgeable about, ultimately what is happening is activation is flowing in particular patterns across the network, and that particular flow is my knowledge of whatever it is I am thinking about. While a different form of thinking about something in this case, which is just thinking about one particular thing and not really about what all I know about it, this just corresponds to which set of nodes are active at that particular moment without any concern about where that activation is going to flow next. So knowledge is all about how it flows across many different sets of units, whereas thinking about something in particular is just what particular set of activation and nodes are active at that moment in time. Thus, learning or changing our knowledge of something must involve some adjustment of the connections among nodes so that after learning, activation will flow in a fashion that can represent this newly gained knowledge. So let's say I think the correct answer to something is A, and I learn over the course of a lecture or an exam that in fact, no, that is not true. Some other piece of information is actually the truth there. I update the weights in my system, not consciously, of course, in that sense, but by updating the weights or connections between the different units, the next time I come across that concept, my flow of activation is now likely to flow towards this new piece of information I have now learned, as opposed to the old one I had previously understood to be true. And this is how we believe that most learning takes place.